problem 1.18 and 1.19. We're all at the end of the chapter. So problem 1.18 says, consider the network in figure 1.8. The frequency transfer function is h of f. An impulse d of t is applied at the impulse. Show that the response y of t is at the output is the inverse Fourier transform of h of f. Alright, so what is the system what they talking about here? So figure 1.8, so let's go. Actually, we're not even going to do knowns and unknowns for this problem because there's only really one known given. We have a system, right? We have a system. In that system, we have an input, which is x of t, so some input value, and it goes into this linear network, which this is a linear network, so this network does something to the signal x of t to change it in some way. And then at the output of that, once it goes through this input, or this network here, which we're going to call h of t, at the output here we have y of t. So y of t is a function of x of t times multiplied by whatever this network is. This is, whenever you have a block here and you have an input into a block, it's almost like doing multiplication in the time domain. So h of t changes x of t by h of t amount, and y of t is the output of that change. Specifically what I'm saying is y of t is going to be equal to x of t times h of t, right? Let's switch to black to see if my black is working. Right, so this is our function here. Now, what h of t usually represents, it represents usually, and we can show this here, so, oh, black is working well today. So h of t, let's do lowercase h of t. H of t, if we divide it on both sides, is y of t over x of t. So the output over the input, h of t tells us how the output changes based on the input. And so that change is this network here in between the input and output, where we alter the signal in between. But before we go there, I want to point that out. That's why we're talking about h of f and h of t. What is h of t? H of t represents the output versus the input and what that change is. So before we go there, we are going to first take this to the frequency domain because it's going to be a little bit easier here. But in the frequency domain, right, when you have multiplication of the time domain, it's convolution in the frequency domain. And so that can be shown like this. So when we go to the frequency domain, we usually use the notation y of f, where f is equal to frequency, or 2 pi omega, where omega is the angular rotation, something like that. That's what omega is. But here we use f to simplify it. So we have x of f, and we have multiplication in time domain, so this is going to be convolution in the frequency domain. We have h of f, right? Now we know here that our input, so our input for x of t here, they said the problem, our input for x of t is going to be a Dirac delta. And that's what's known as an impulse, impulse. And they usually, when you plug in delta t for x of t, it's called an impulse response. The reason is because you want to see how the system reacts when you do a quick little burst of energy, or a quick little burst of a small infinitesimal large value gets input into the system, and how does it react? And that gives you kind of a baseline for what your system actually is doing. And so here we have delta of t. Now, if this was delta of t, what we can do is we say, well, we know if we have an input here and we take the Fourier transform of the input, here it'll be the Fourier transform of this input convolved with h of f. So here we can substitute this with the Fourier transform of x of f, or x of t rather, convolved with h of f. And we know the Fourier transform of this is x of t here for this example is delta of t, convolved with h of f. And we know here that delta of t, the Fourier transform of delta of t is 1, so this ends up being 1 convolved with h of f. Correct? That's correct. Now anything convolved, multiplied, divided, anything of that nature is going to be equal to h of f. So 1 convolved with h of f is just h of f. So essentially what we have here, we have y of f is equal to h of f. So that means the impulse response is the inverse Fourier transform of this, because when you take the inverse Fourier transform, you get the time domain representation. So basically what I'm saying is, when you take the, so going up here, when you take the inverse Fourier transform, so take it back to the time domain, that's what inverse Fourier transform means, taking it from the frequency domain back to the time domain, you're going to end up getting y of t. Because here, this is when you take the inverse Fourier, h of f is equal to y of f, so you could even put y of f here if you wanted to extend it further, then you could put, and you would get h of t, for example, which is equal to y of t here. Right? So this is essentially what this problem is asking for. It just wants us to show this whole process, and we showed that. So we showed the network. The network equation is y of t is equal to x of t times whatever the linear network does to manipulate it. Then we plugged in a delta of t for our input for x of t into this network, and we saw the delta of t, the Fourier transform of that is 1. So anything multiplied by 1 would just be, or convolved with 1 would just be itself. So in the end we get h of f. So then h of f is equal to y of f. H of f is directly equal to y of t when you have an input of delta of t. And you take the inverse Fourier transform of that, you're going to get y of t because y of f is equal to h of f. And so the inverse Fourier transform of y of f or inverse Fourier transform of h of f is equal to y of t and h of t. So that's really it. That problem is really simple, straight to the point. Now let's go ahead and do the next problem. An example of a holding circuit commonly used in pulse systems is shown in the figure P.12. Determine the impulse response of the circuit. So here we go, another circuits problem. So with this problem, we have an input. It's x of t, and it's going into the system. It branches off, so it branches off, and it has a delay of t0. So that's going to be an input, and then it goes all the way over here. This input goes here, and the delayed version goes here. Goes into what's called a summer. So we can use that. Then you have a plus, you have a minus. Then it goes into an integrator. So integrator. You all get the idea. This little guy. Boop. And then it goes out into y of t. So let's write the equation for this one. They call this part g of t. Let's write the equation for this. Let's break it down. So let's solve for g of t first, because we know that y of t, right, is going to be the integration of g of t, because that's what's going into the integrator, g of t, and that's what y of t gets. You just follow the chain, right? So go backwards. Y of t is here, so y of t has to be the integration of something. Well, that integration of something is g of t. That's what g of t goes into the integrator. So y of t is the integration of g of t. Well, let's figure out what g of t is. So the integral of x of t is going in, and then it's getting subtracted by the delayed version of x of t. So we have x of t going in, subtracted, because this is a, you see the summary, there's a plus and minus sign, so this is going to be plus the minus version of this, so it's going to be x, and this is x of t, but it's a delayed version, so it's going to be x of t minus t naught, where t naught is a delayed version of it. Okay. So now what we do here is we say, all right, this is our y of t. Now, they want us to find the impulse response of this. So once again, they want us to plug delta of t in for x of t and solve. So we could do the Fourier version of this, but it's going to be easier to do it in the time domain here in this case. Sometimes it's easier to do in the Fourier, sometimes it's easier to do in the time domain. Here it's going to be easier to do in the time domain, right? This is from minus infinity to some value, let's say, let's just say a value here, let's say it's t, right? So let's break this integral up, because this is a subtraction, so we can subtract these integrations up. This is minus infinity to t, which is the current period whenever we're actually doing this integration here, and then minus infinity. I mean, t may be confusing, but you guys get it, right? That t is, this time frame might be different than this when this integration happens. There's a slight, there's a slight delay in between this signal getting in, delaying, adding, and there's basically some time difference between when it gets here and when it goes over here. So I use t, but really t is different here from the exact moment where this enters. So for this integral, right, we know that the integration of delta of t, so let's make a little note here. The integration of delta of t from infinity to infinity is delta of t, right? Oh, it's delta of t, correct? We know that this integral is equal to 1, so it's constant for all values. That's basically the area underneath the delta curve, the Dirac delta function is equal to 1 for all time frames. For our case, we're going to consider that the signal starts at some, because the signal it doesn't go from negative, it goes from, we're going to assume that it starts at some time frame, and then it goes to, it doesn't go for all eternity. It starts somewhere and then it goes to t. And this one starts somewhere and goes to t. So in this case, when you have the integral from minus infinity to some value t of delta of t, to t, right? Or we could even use tau here. We're going to just differentiate it. It's going to be equal to basically what you get as a step function. And the reason you get a step function is the step function is constant, right, for all values from 0 to infinity. And so you'll notice that the function is not 1 for all time frames, it's only 1 for a portion of the time frame, because here we're limiting the bounds of the delta, the Dirac delta. So it can't be 1 for all time because we limited the integration inside the delta. So that's just a quick note. So here what we're going to end up getting is, we know this one's going to be u of t, right? Now this one has a time shift. So this is going to shift our delta it's going to shift our unit step function by this time shift. And so over here we're going to get plus u of t minus t naught. And so here we have two step functions added with one another. So let's draw a graph here. That may make us clear what there's going. So look, we have a unit step function that starts at 0, goes up, and then goes to all infinity, right? And then you have another step function that's delayed by some time frame. We'll call it t naught. And it goes here, and then goes up for all time. Now when you add these together, right, or rather, I'm sorry, when we subtract, these are being subtracted. I put an addition here, these are subtraction here. This subtraction sign goes in between. Now when you subtract these together, right, this part, in this area here, they're both 1. So it's going to be 1 minus 1 is going to be 0. So this part cancels out. And over here, 0 minus 0 is going to cancel out. But in between this part, this section right here, right, it's 1 minus 0, because the delayed version is 0 here, and the one center at 0, at t equals 0, is 1 there. So there we're going to have a box, essentially. And so we know that a box, we have a form or equation for a box. It's called rect. So we have a rect, so our y of t is going to be equal to rect. Right, so it's going to be a rectangle function, right? Some sort of box function where this area is the box. So this is 0, and this is t0. So there's going to be time t, because the y of t is in time t. And this shift, right? So we shift this. The box is always centered at some place. When it's centered at 0, it's just rect of t divided by whatever the distance of, or the duration of the rectangle is, whatever the width of the rectangle is. But here, the box is centered in between 0 and t naught. So in between 0 and t naught is equal to the in between of this right here, right? This line in between the box is t naught divided by 2. So this is going to t minus t naught divided by 2. T naught divided by 2 is the center. And then we need the duration of the box, the width. This width is 0 to t naught, so it's going to be t naught minus 0, which is just t naught. And that's going to be our final function to represent y of t, which is going to basically be what y of t is, given that x of t is the delta of t. So you're going to end up having a holding circuit that generates a rectangle when you input a pulse here. Now if you input something else like a rectangle, you may get a different response. But here, our response here, it's going to hold the value underneath essentially underneath this x of t input and the delayed version of it. Well, here we know that the integration underneath a delta of t is 1. And so it's going to hold a constant 1 for some time period, and then it's going to stop. And that's exactly what it does. So you've got a holding circuit. It held the constant value of 1 after integrating underneath the curve with this value. And this is obviously quite useful for things like, trying to, when you're integrating like energies and things of that, and you're trying to figure out what symbol or what value was sent, on the receiver side, on the transmit side, and you're on the receiver side, what value was sent. You have to integrate the signal. This could be one application. There's lots of other different applications for this specific circuit here that's being used. I mean, it's a very simplified version. So anyway, that's this problem. Hope you guys enjoyed. Hope that was helpful to you. And yeah, that's it.